So, welcome back to Advanced Algorithms. The last lecture finished with a deadly tendinous cliffhanger on Quicksort. So we've been in the middle of a proof when the time was up. Just to recall, we've been talking about Quicksort in the randomized version, which means that we pick the pivots from random positions. And we were talking about a statement in this with high probability language, which essentially means a very good bound on the probability, namely, a polynomial decrease, if you like, n to the minus c for any c. And depending on the c, the constant for the bound that we claim, namely for this big O, is might change. So the formal statement of what we were proving was this. If we consider these recursion trees in Quicksort, they are generated by putting the pivot of each partitioning step in the root, and then the two recursive calls generate the subtrees. Then the height of this tree is O of log n with high probability, which, because we spend at most n comparisons, so I didn't really, okay, yes, here it says comparisons, right? That's fine. Other cost measures are similar. But yeah, to be specific, we spend at most n comparisons on each of the levels of the tree. If there's no more than logarithmic levels, that means we are close to the expected we are in the expected complexity and close to the expectation also, because there's only a constant missing. We started the proof by introducing the notation there's nodes in this recursion tree that have a certain number of elements and a certain number of, so in the whole subtree, and they have a left child, which we needed to express a certain balancing condition. We call the node balanced if it either didn't require a recursive call, or if the left and right child were at least 1/4 of all elements. And that meant that we could bound on any path in the tree the number of such balanced nodes, because every balanced node reduces the size of the list of elements still to be sorted by at least the factor 3/4. And that means we can't have more than 3.5 ln n such balanced nodes on a path in any tree that has in total just n elements. So that was a very simple idea. And we finished with introducing for such a path these indicator random variables that just ask whether the node at this depth is balanced. And I claimed that there's a problem that we cannot apply Turnoff's bound to the sum of these random variables because they are not independent. So one thing that is independent is the choice of the pivots. This is the basic assumption we made about the algorithm. At each partitioning step, we choose the pivot independent of all previous choices for the pivot. But the independence comes through a backdoor, because these xi, probability that such a node is balanced, depends on the size of this node. Why so? It seems like we just removed that by dividing here. But there's a discretization problem. Okay, let's look at a few small examples. Say we have a node with 4 elements. Then what we require is that j divided by n is in 1/4, 3/4, with less or equal. And if the, well, so this, I should write off v in both cases. If now this is 4, we can multiply through, and it means that this is exactly fulfilled if we have something in 1, between 1 and 3. So here the probability would be, for a balanced node, would be 3 over 4, because what's the values that the j can take? It can be anything between 0 and 3. If you have 4 elements. Okay, let's make it a bit nicer. So you can pick any of these 4 positions as your pivot. And if you pick this, then the left part is just empty. Whereas if you pick this, then the left part is 2, and the largest you can get is 3. Okay? So because j was the size, the number of elements in the left recursive call. Is that clear? So that was for one example of a subtree size. If we go to 5, we can ask the same question. So this remains the same. But because we now have 5, you can check that there's only 2 possibilities in that case. And that means there's just 2 out of 5 possible pivot choices that makes this node balanced. Okay? Maybe you want to see a few more. One more that I prepared is, so for 8, you have everything between 2 and 6. So here it gives you 5 over 8 as the probability. And this is a problem because if you now have, say, a list of size 10, then the probability that its left child node is balanced depends on the size of the sublist of this left node. And that in turn depends implicitly on whether the pivot for this 10-element list was balanced. Right? Or more formally speaking, independent events require that the probability is factor. If you say we'd need, for example, that the probability that x1 is 1 and x2 is 1. This must be just the product of the individual probabilities. But now if x1 is balanced, there's certain subtree size, subproblem sizes that are impossible for x2. And if it's the other way around, if this is not balanced, then there's also certain sizes that are excluded here. And because most sizes yield a different probability for these balanced nodes, the events will be dependent, but only in a very, very harmless sense, actually. It's only because of this discretization differences. Okay? But they are not independent, which is very unfortunate. You may think a second about how one might fix this, because they are mostly independent. All the randomness is actually independent. The choices of the pivots are done independently. It's just this obnoxious probabilities. Okay. One thing that we can note at this point is the probability for a node to be balanced certainly only depends on the length of the sublist. It does not depend on the numbers that are in this sublist, and also not quite where in the tree this node is. The only problem is that the size of the sublist determines this discretization effect, right? So we can define the probability for a node to be balanced, given that its size is exactly this n. So the B stands for balanced, right? And one thing you can show is that this is always at least 2 over 5, which in a sense is exactly the value that you have for n equals 5. And then for all others, you can check that it's actually larger. In fact, it's clear if you ever increase n, then the discretization effects become smaller and smaller. And well, in the limit, this probability should be 1/2, because it's exactly half of the values of j that we require, that we regard as balanced in the limit. And then that means that the differences from this limit go down, so you only have to check the first few values to find the smallest one. So that's at least something for all n greater or equal to 1, actually. So that's at least a good thing. We can lower bound the probability for a balanced node. And in the end, that will be sufficient from an intuitive point of view, but we still have non-independent events, dependent events, but we want to apply Turnoff's bounce, so we have to make these events independent. And the best would be IID, then we can just apply the simplest Turnoff bound, namely that for the binomial distribution. And that's actually a very simple trick. We call a node good, which is a new kind of quality, whenever it is balanced. And if it is balanced, we also flip a coin with a very specific probability and check if that coin gives us heads. Now, P is a constant that we pick, which is just this minimum value here. Thereby, we know that this is always in 0, 1. And we assume that all these coin flips that are ever done are independent of each other. I mean, that's a natural thing to assume, but just to mention it once, okay? And now we define new indicator variables. Called GI, which is just the indicators for this event that the ith node on such a path. So I haven't formally defined the V, so that will follow in a second. But if you can imagine, if you have a path of nodes that start at the root and go down to some leaf, and these are called VIs, then each of these can be good or not, depending on the partitioning choices. And you can call these, you can define these indicator events. Now, these indeed are independent because the random processes are independent, the pivots are chosen independent, and these coin flips are independent. And they also have the same probability at each step, because this is exactly chosen so that the probability is equal. Right? Because the probability that VI is good is the probability for this coin flip. So, okay, let's just write the probability directly. Conditional on the event that this is balanced. So maybe I should write it down properly. So let's call this thing the coin I. Okay, is 1 given xi, which was the event that this node is balanced, times the probability for xi1. And if you just multiply these out, then this is always p. Okay? So the conditioning here is only needed because this coin flip is only done, that's my interpretation of this AND. If the node is not balanced, we forget about the coin flip, and if the node is balanced, then we only do it. We don't need the coin flip if the node is already imbalanced. And thereby we have a sequence of events that are indeed IID, independent and identically distributed. Okay, IID, is that something that is common? So that's just an abbreviation. All these are independent, or it was in part of the independent and identically distributed. It must have occurred in the tail bounce part. So this is already a good progress. There's one more catch, but that's an old trick. That's not my invention. So let's see how this together in the end yields the proof for our result that we are claiming. In the end, we want to say something about the height of this tree. Okay, we want to say the probability that this tree has height more than d times ln n is small enough, and we'll come back to that. For the first step, we just rewrite that because the height of the tree is actually an inconvenient thing. We better talk about paths in the tree. And for a certain height, that's the same as saying there is some path of length at least that. Okay? The height is always the maximum, so there must be some path. And now this exists a path. This is essentially a union over the depth of all leaves in the tree. So this is something that comes from Quicksort. There are at most n leaves in the tree because every partitioning step makes sure that one pivot element is at its final position, which is then no longer part of the recursive calls. So after n steps, all elements have been pivot once, and the whole sorting is finished. Okay? And that means there are at most n leaves in the tree that don't have any recursive calls. Usually there will be less than n, but a simple upper bound like this suffices. And then this is essentially saying there exists a leaf of depth greater or equal this, right? Any path has to go to a leaf. And then because we have at most n leaves, we have at most n independent chances to get to this depth. Well, independent, they're not independent. We have n chances to have a long path. But even if they are not independent, the union bound says we can still upper bound the probability by assuming they are independent. That was one of the very basic tricks, one of the basic inequalities that we had. And now we have reduced this to the probability that any specific leaf has a depth greater than this. And this is easier to handle because for a specific leaf, there's a specific path in the tree that we can follow. So if L is a leaf in the tree, then we denote by V1 up to Vd of L, the depth of L. The last one is exactly L itself. We denote by this the path from the root down to this leaf. So this is the depth of this leaf. That means we have, by this definition up here, we have such a sequence of events, of indicator random variables. And these are actually independent and identically distributed with a Bernoulli distribution, so they are 1 with probability p and 0 otherwise. Now to apply Turnoff's bound, it's a bit inconvenient that this sequence stops here at a certain point, namely this depth of the leaf, where this depth of the leaf is actually what we would like to have in the bound. So in a sense, we are looking for, so here the leaf has depth so and so, we can just write this as d of L, right? Now we would like to have a bound where this d appears inside of this. And it's inconvenient that it's the end of the sequence at this point. Therefore, we simply extend this. So this sequence is tied to a specific execution of randomized quicksort. And now we fill this up to an infinite sequence by just adding new random coin flips. Can you imagine what I mean? So we have this sequence whose length is actually random because it depends on the tree. But no matter where it stops, we can just add new such variables, each of which has this distribution that the others also have, only that these are not related to the tree, but are just given by some independent coin flips.
Is that supposed to be a +1?
This is a +1, yeah. Okay. Subscripts are already too small. Okay, now we are finally in a position where we can apply our tail bounds. Because now we can, for every number h that we pick, we can take the first h of these g's and sum them up. And if we do that, we get something that has a binomial distribution, just by definition. The binomial distribution with h trials and probability p's is exactly the number of successes when you try h times and succeed in each step with probability p independently and identically for all the trials. And this is exactly what we're doing here. And for binomial distributions, we can apply our Turnoff bound. So just to quickly go back, there it is. If we have a binomially distributed variable, then we can normalize it by dividing by n and subtracting p, which is essentially the normalized expectation. So p is the expectation of each of these individual axes. Then we can bound that this is far away, well, is far away from 0 by a very good bound. So that's what we use. So the probability that our specified leaf has a longer path than a given number h. That's at most the probability that the sum of the first h g's is less or equal than 3.5 ln n. Because the sum is the number of good nodes. And, well, every good node is also a balanced node, because a good node was one that is balanced and additionally has this lucky coin flip that succeeded. Good means balanced and something else. So if we have more than, if this is the number of balanced nodes, or, well, a lower bound for that, then we can't have more than this magic number. Otherwise, we contradict our idea here, right? Any path in such a tree with n elements can have at most so many balanced nodes. So if this leaf is to have this depth h, then there can't be more than, well, on the first h g's, we can't have more than so many ones. Now let's give this a name xh, which has this distribution. It's just more convenient for the next steps. Now we can rewrite in this this condition a bit. If we flip it and add p on both sides, then and we divide by h, okay, quite a few steps. So we divide by h, then we get this, and then we multiply by -1, and then we add p. Then what we get is this. We have to divide by h. Okay, that's just an algebraic reformulation of this inequality, which leaves then the probability unchanged. The next step is to add absolute value bars here, which then means that inside we can also exchange these two. And we call this thing delta. Okay. Then we get something that is of the form where our Turnoff bound applies. But we require at this point, if we want to use it, then we need that this is positive. So here we assume that delta is well, it can be 0, but it's not negative. And we will later have to check that for the values h that we use, this is actually fulfilled. And if we assume that this is true, then we can use this Turnoff bound from above. Which had exactly this form. Only that this was n, but now we have the parameter of the binomial distribution was h instead of n. Now this kind of holds for every h, so that this is fulfilled. but we will use it for the height that we're claiming in the statement of the theorem, which was with high probability O of log n. So let's just pick some constant d and say h is d times log n. That means delta, which is p. So p was just the 2 over 5, right? The lower bound for an individual node to be balanced. Minus, well, and now we can cancel the ln n at this point. So here the ln n is gone, and we're just left with that. And this is indeed larger than 0 if d is at least 8.25. You just check that this is the right number. So that means we can't prove anything about the height of the tree if we're too ambitious. If we would like to have a too small coefficient in front of the ln n, then the method will not work. But for the statement, this with high probability bound, this is fine, because we just said there is some d for every exponent of the error bound for the probability. Okay? It's fine that the d has to be of a certain minimum size. So that's almost the end of the proof now. The probability that the tree has height more than this, d ln n, was n different leaves times the chance that any of these leaves has a depth more than d ln n. And then we use the Turnoff bound from above. So minus 2 no, this h doesn't make sense. Okay, we can just leave the delta as it is. That's more convenient than to insert its definition. But what we have here is we have an ln n in the exponent and an e to the and so on. So this is nothing but n to the minus rest, okay? And we have another n over here. So in total, this is n to the 1 minus, and then this remaining part. And this is essentially the end, but maybe we should check that this is actually yielding us what we claimed. So the point is that this function, if we are given any constant c, so we can make this probability that the tree has height greater than this. We can make this arbitrarily small by choosing a large enough d. So the delta only says d has to have this minimum value. So we can make this to be an O of n to the minus c. If we just pick a d such that this 1 minus 2d delta squared is less than minus c. Okay. Which you can make, it's 1 plus c divided, oh, that's why I didn't write it down. Okay. The point is that the delta also depends on the d. But you can pick a large enough d so that this is fulfilled, even though it's a bit inconvenient to write down the explicit term. And that basically concludes the proof of this with high probability statement. The way to view this is maybe nicer if you turn it around. You first supply a value of d that you would like to have, and then you check what's the best bound on the probability you can give. And I think one specific example is helpful to see that there's not humongous non-realistic numbers involved. So for example, that the height is 42 ln n, gives a probability bound of n to the minus 7.4, which is really a very, very small probability, right? So n to the minus 7.4. So for large n, this is essentially less likely than that some hardware problem makes your computation break down. And 42 ln n is not astronomic, okay? Okay, just finish this. That's just random. It's 42 because it's awesome. The other way around is actually easy. If you just insert a d here, then you get a c back, right? You just have to compute these wicked numbers, which I'm not able to do in my mind, but I checked with a calculator for 42, and you might check for other values. There's a lower bound for d so that this doesn't work. If d is too small, then the c you will get is actually not negative up here. So if you're too ambitious, if you just say this, I would like to show that height is less than ln n without a factor, then you won't get a probability because that's basically impossible. And this makes sense. It would be fishy if that would work for any kind of coefficient. But I just wanted to give you one concrete example to show that it's not 10 million. I think this means we can rely on Quicksort quite a lot, because it's not only that its worst case complexity is bad, but kind of unlikely. It's almost for sure that you will stay within a constant factor of the best case, actually, right? We can rely on randomized Quicksort. That's a good point. Yeah, you should definitely do randomization. Unfortunately, I have to say that I don't know any programming library that actually uses randomized Quicksort. They all rely on luck or another trick. So it's a good point. Well, there's two answers why this is not a problem in practice. The first is you can replace randomized Quicksort by the assumption that the input is in random order, which sometimes it is, and if it's not, you might just consider shuffling it before, which is actually a concise implementation of randomized Quicksort. First shuffle the input, then sort it. Yeah, it might sound like it's a bad idea, but it gives you a safeguard against bad cases. What's also done in practice is another simple trick to avoid at least bad cases. So in practice, people use intro sort to safeguard against the bad case by just keep a count of the recursion depth. And say you start with something like 3 ln n, then you count down whenever you go a recursive step down. And if you reach 0, then you say, oh my god, this must be a bad input, let's just do heap sort. And you abort the recursion. That's what's usually done in practice. If you choose this height bound a bit conservative, then it will not often be used, but you can avoid algorithmic complexity attacks. So these are actually real scenarios that web servers are attacked by supplying them with things that make algorithms go to their worst case. I don't know any actual attacks on Quicksort, but for hashing, this has been used. If you use hashing without randomization, then you can make it, instead of worst case constant time, you can get linear time, right, for each insert. And there have been attacks reported to web servers by just supplying things that make it hash into a bad case. Then it was like an effective denial of service attack. So Java for a long time didn't use that. So the Quicksort in Java was susceptible to such attacks. Just with a new version that's coming in a few months, it will be changed. Okay, that was kind of a digression on Quicksort. Another application of these tail bounds is a way to improve the probability guarantees for other kinds of algorithms. So Quicksort can be seen as a Las Vegas algorithm because it's never wrong. But even if you have algorithms that make errors, you can improve. So the original definition of a Monte Carlo algorithm was that it can produce a wrong result every other run, which is maybe not very helpful in practice. And you can't just simply repeat it in the way we did with Las Vegas algorithms, because it's not clear when to stop, because we don't have this question mark output, but we just get a wrong answer and don't know whether a given answer is wrong or right by just looking at the outcome. But we can use the following simple algorithm, which is called majority voting. You run such a Monte Carlo algorithm for t times, and you check if there's a majority outcome. If the outcomes agree with an absolute majority for some value y, then you return that. And otherwise, you say, sorry, no result, try again. Okay. Now we had two different kinds of Monte Carlo algorithms, the ones with bounded and the ones with unbounded errors. The bounded ones had bounded error says they fail with probability less than 1/2 minus epsilon, or maybe the other way around would be nicer. So that's the way we defined it. Success with success probability is at least 1/2 plus epsilon for some constant epsilon that doesn't depend on the input size or input. Whereas we also had the unbounded error Monte Carlo. There we had the same, where we just said something greater than 1/2. And I added the remark that there's a huge difference between the two. And we will hopefully today see two reasons that make these two definitions very different. And the first one is this. If we use majority voting for a Monte Carlo algorithm with bounded error, then we can use quite few repetitions, just a bit more than logarithmic. So for example, you can use log squared of n, right, which is still a reasonable number. And then you get an algorithm that is correct with high probability, in just the sense we used it for the quicksort analysis now. And no, log squared is just log n and then squared, right? Whereas log of n would usually be log n, chicken theorems, log. So this is the default way it's written in TCS, right? So but you're right, it's a bit sloppy to omit all the parentheses. So let's also prove this. I promise the proof will be nowhere near as long as the first one. But it will use the same techniques. And the printed lecture notes that I gave to some of you, there's a different proof that's much more, much more work. And actually, it's a simple application of Turnoff Bounce again. So we have again our indicator variables x, where this time x means that the ith run yields the correct result. Okay. So we're looking at the function f. So there's one specified output that's correct, and everything else is wrong. But we don't know which one it is. But we know that these are Bernoulli distributed with a certain probability. And from the definition, we know that the probability is at least 1/2 plus epsilon. But here we just say it's exactly 1/2 plus epsilon. If by any chance this probability for the algorithm to be correct depended on the input size, as it did in the quicksort case, then we might have a different epsilon here for every input. But in this case, it's not a problem because we repeat the algorithm on the same input. Okay? So we know there's a certain, so we know that epsilon, there's a lower bound for epsilon that does not depend on the input. And it might be that this epsilon is a different one for each input, but it's the same in all the repetitions of our algorithm here on a single input. So we don't have the problem that we just had with the dependent random variables. Okay, that just means the sum of these is binomially distributed with t repetitions and probability p each. So we can directly apply Turnoff Bounce. And the majority vote fails. Maybe I didn't make that clear here. So the trick with the majority vote is that if there's an output that's returned by the majority, then there's just one such output, right? There's no ambiguity. And the algorithm can fail in essentially two ways. It could return a wrong result because by chance more than half of the outcomes were a wrong answer. Or it could be that we return don't care or don't know in this case because there was no majority output. But with these indicator random variables, we treat both cases the same because they're only one if the outcome of a single run is exactly the right one. Okay, there's two ways for this to fail, but they can be expressed by the same variables. Namely, it fails whenever this is less than t half, which could mean there's no majority at all, or there's a wrong majority. And you can check that this is, okay, this is trivial, I'm sorry. It's the next step. It's less than equal, but it's strictly less, and it's an integer, and then it's less than the same thing, -1. So what's the probability for x to be strictly less than t half? So the probability to fail is at most so we can weaken this slightly, at most this. Now we again do the similar trick as before. We rewrite the condition inside by dividing by t, and multiplying by -1 and adding p. It's essentially the same step as we did before, so I'm fast forwarding a bit. Then again, we take, on the left-hand side, we take absolute values. Okay. And if this is greater than p minus 1/2, this here, so this only makes the requirement weaker, and thus the probability greater. Now by our definition above here, this is exactly epsilon, which was greater than 0. So we can apply the Turnoff bound in the same way as before. And get this result. So we've proven a bound on the probability that we fail with our majority vote. For the with high probability thing, we have to show that this is actually in O of n to the minus c for all c's. So what we show is we multiply by n to the c and check that this goes to 0. So that the majority vote fails, even if I amplify that probability with a polynomial factor. I can still use this. So if I put this into the x, then I have c ln n. If you pull it out again, you get this. And minus epsilon squared t. So what we have to show is that this goes to 0. So we want that this goes to 0 as n goes to infinity, because then we have the probability that this fails. It's actually in small o of n to the minus c even. And we would like to have this for any c. So c should be arbitrary. So this term goes to 0 if the argument of the exponential function goes to minus infinity, right? And this goes to minus infinity whenever this grows faster than this. So if we make t grow strictly faster than logarithmic, then this term will eventually dominate whatever is on this side. And the constant c here actually doesn't matter. So if we make that assumption, that was what we had in the assumption of the theorem, then this goes to minus infinity, so the whole term goes to 0. Well, that is already the proof. Now in the theorem, we only said the majority vote is correct with high probability, which is only a statement in the asymptotic sense. But you actually, with the Turnoff bound here, you also get a bound on the probability to fail that is not asymptotic. The Turnoff bound is just an inequality. And if you insert any number of repetitions that you pick for your specific algorithm, then you also get a specific error bound here. Okay? So we actually proved a bit more than I claimed. But for the sake of showing the difference between bounded and unbounded error, this is sufficient. And let me point out again that logarithmic number of repetitions essentially means you need something like a log squared factor in the running time to get a very good algorithm. With high probability, this is sufficient in practice because the error bound is for the probability is actually like a hardware failure. Whereas usual algorithms have linear or maybe quadratic running time, then adding a log squared factor is not so much of a problem. So bounded error Monte Carlo algorithms are actually usable. Now let's look at the unbounded error case. And here I only show a negative result. That's a bit tough to read, but it's actually a simple statement. So it says in the worst case, so there are Monte Carlo algorithms with unbounded errors. And even if they use only a linear number of random bits, which is not so much, you can't even shuffle a list with a linear number of random bits. So it's usually you need more random bits than that. But as a worst case or counterexample, it suffices to say, let's say random is linear. And if you would then want a guarantee for the majority vote to succeed, that's not even with high probability, but just some fixed delta, which can be, so, well, this is the failure probability. Sorry, though. Let's say this is, can we, okay. And the delta should be between 1/2 and 1. So the statement is, I would like to amplify the success probability of an unbounded error Monte Carlo algorithm. And the theorem says I can only do so with a very high number of repetitions, namely superpolynomial. It's not even sufficient for any fixed c to take n to the c repetitions. At least for a specific bad example of this algorithm. So in general, if you have any kind of Monte Carlo with unbounded error, you don't know. You can't guarantee a good error bound without super polynomial number of repetitions, which makes it unusable. Okay. So for the proof, the core part is that unbounded error meant success probability is just greater 1/2, but we don't know by much. And in general, if you have a certain number of random bits, and well, we're now in the case that we assume that the algorithm is always terminating. So it never uses an infinite number of random bits, but random is finite. So in our specific case, it's even linear. But in general, even if it's only finite, you know that A has at most 2 to the number of random bits different runs. Well, at most, and also up to, in the sense that for the worst case, all of these runs are different on a specific input x, right? That's just what can happen. And each of these runs has then this probability 2 to the minus random a. Well, if we now assume that this is actually just n, so one instance for that, so this is 2 to the n, this is 2 to the minus n. It shouldn't come as a surprise that we can have an exponential number of different runs. That's the same that we had for non-determinism. So as above, the probability, or just the event that the majority vote fails, is that this x is less than t half, where x again is binomially distributed. T times, we repeat something, and the probability to succeed is p. But now p, in that case, the worst thing that can happen, we know that p is greater than 1/2, but nothing more. And the worst thing that can happen is that exactly one more of these runs than half are successful, and all others are failing for a single run. So it could be exactly like this. Okay. And we'll again denote this by epsilon, but actually this now depends on n, and it drops very quickly. So I think after this explanation, you might already believe that this is a bad thing, because the success probability goes to 1/2 very, very quickly. So it will, in most cases, you will just not have a majority of outputs. If it's like 1/2, 1/2 to have either output, then there's a good chance that you will not have one that actually is output more than half of the cases, more than half of the total number of repetitions. And that will be the essential problem. To show that, this is actually a lower bound for this probability. So we will want to show that this fails with at least a certain probability, whereas before we showed at most with a certain probability. And therefore, Turnoff's bound is not helpful in this case. It doesn't help you here. But we need to go by foot in a sense. So what we will show is that the probability that x is in a very specific small range, namely between t over 2 and its expectation. We'll show that this probability is sufficiently small, namely satisfies this kind of strange magic bound. And then we'll use that the binomial distribution, in general, binomial distribution is symmetric. So the probability to lie on the left side of the expectation is roughly 1/2. We have x less or equal e of x with at least 1/2 probability, just because the two halves are symmetric. And from these two ingredients, we can show that the probability that the majority vote fails, which is nothing else than this, so we can slightly weaken this again by saying x is strictly less than this. And this we can express as, okay, maybe next line. The probability to be left of the expectation minus that we are left of the expectation, but above the t half. So this is just, graphically speaking, here in the middle is the expected value. Or maybe not exactly in the middle, because p is a bit larger than 1/2. And here's the middle, that's actually t1/2. And now the first probability says we're in this left half. And to be smaller than this just means subtract that little part here. And then using this bound, this is just 1/2, or at least 1/2. And this is at most this. And we find this lower bound for the failure probability. And if we just insert the values, so we say we take n to the c repetitions, and the worst case epsilon was just one run more than the failing ones is accepting, so that was exactly what we had here. The probability for a single run to succeed is just a tiny bit over 1/2. And with these two numbers, you see that epsilon t goes to 0 because just this dominates the polynomial part. And then also this goes to 0 because this goes to 1, but then it's multiplied by 0. And then that means that this whole thing goes to 1/2. So for these parameters, the ones that we claimed, you can show that the probability for a failure goes to 1/2. And that means you can't amplify the probability, at least if you only pick a polynomial number of repetitions. So there's one thing we skipped yet, and that's the proof for this inequality up here. That's what we still have to do. So, okay, we can rewrite that x is between t1/2, and the expected value is just t times p, and p was 1/2 plus epsilon. And we wanted to show that this is this strange term epsilon t, 3 to the epsilon t. Now this probability, okay, let me just be lazy, I don't copy it again. Just by the definition, we sum over all values that this can take. t1/2 plus epsilon t. And then the probability for the binomial distribution is this. The number of ways to pick I elements from t. Probability that exactly I of them are successes and all others are failures is given by that. That's just by definition. And now essentially we only have a very small slice of this sum. And that means we can simply upper bound these terms individually, and it's sufficient. So you know that the binomial coefficient, if you sum over all I, then it sums to 2 to the t. Because this counts the subsets of exactly I elements, and all subsets are just 2 to the t. So we can be very generous. So this is less or equal 2 to the t. We can be very generous by estimating it like that. t1/2 plus epsilon t, 2 to the t. For this term, that's a number smaller than 1, so we can make it larger by picking the smallest exponent that we can have. And let's actually just pick one smaller even, 1/2 plus epsilon to the t1/2. And similar here, but and because we have a minus, the smallest exponent is actually here, the largest value for I. So we have t half minus epsilon t. Now you see that these terms don't depend on this summation index I anymore, so we can just have epsilon t times the same term. And then we have, so this can be written as 4 to the t half if we like. Then we have a part with the same exponent from each. We just combine these. 4 times 1/2 plus epsilon, 1/2 minus epsilon to the t half. And then we only have these left. You can simplify this. That's binomial formulas and so on, right? This is 1 minus 4 epsilon squared, which is less than 1. So for an upper bound, we can just replace the basis here by 1, so then the whole term vanishes, and what remains is epsilon t, 1, and this term. Well, and in this term, you can show, so epsilon can be, is 2 to the, that was our 2 to the minus n. So you can just show that this is larger than 1/3 for n at least 3. And then you have 1/3 to the minus, that's the same as 3 to the epsilon t. So this is what we claimed. And with that together we proved this small slice has this probability at most that combines with the proof. Okay. New page would not be necessary. This shows that unbounded error is not very helpful because you can't even amplify the success probability a bit. And, well, next time we will also see the second reason why the difference between bounded and unbounded error is so big. Well, this statement is a bit pessimistic because maybe some unbounded error actually has a better guarantee than we can prove. But if you can only show unbounded, there's not so much to do. Since we started a bit late, I think I have a few minutes left to give a few definitions, and maybe then next time we'll continue with the proofs from that part. We talked about the classification of randomized algorithms in Las Vegas methods and Monte Carlo methods, where we allow or disallow errors. And we've seen that if you allow errors, you have to be very careful what kind of success guarantee you give. To make that a bit more specific, there's also randomized complexity classes that give us some insight on which kinds of randomization, which parts of a randomized algorithm are helpful and which are actually not making a very big difference. And we'll briefly discuss that. The theory is not as complete as the general P versus NP or the theory in the FPT part. Maybe I can hint at why. So we're back to decision problems, which means that from now on we only have these 3 different outputs. The input is not in the language, the input is in the language, or I don't know. We just keep that because we had that for the Las Vegas methods. And it's you can show that in terms of the complexity theory, it doesn't help a lot if random is very small. So we just assume that every single step in the computation draws a random bit. Even it might not need that. It just makes the definitions a bit simpler. Then we have 3 different classes of languages which correspond to the 3 different types of randomized algorithms that we've introduced up to now. ZPP, which stands for Zero Error Probabilistic Polytime, is the set of all languages for which we have a Las Vegas methods, a Las Vegas algorithm. And zero error just means Las Vegas, right? So written again here, the probability to be of the same result as this Iverson bracket of x in L, so 0 or 1, when it's not in the language or in the language, respectively. And polytime means worst case polytime in that sense. So we're excluding this case that an algorithm runs forever. We already proved for Las Vegas methods, or you will prove in the exercises, but we stated the result in class that for Las Vegas methods you can always avoid the case to run forever by allowing that's a very bad idea. Greater equal 1/2. I'm sorry, so this is vital. The algorithm has to be correct with probability 1/2. And if it's not correct, it must say question mark. It can never return the wrong result. Okay, if x is in the language, the result is either 1 or question mark, and if it's not in the language, it's 0 or question mark, and we have this probability bound. So must be like this. So we allow question mark with a certain probability, but for that, we fix the worst case time to some polynomial. Okay. Then we have the same kind of classes for the Monte Carlo methods. BPP is for the bounded error Monte Carlo algorithms, and it stands for bounded error probabilistic polytime. Whereas just PP stands for only probabilistic polytime and corresponds to unbounded error Monte Carlo methods. Now if you think back to the result that we've just proven, namely that for these guys we can't even amplify a bit the probability, whereas for these guys we could even show a with high probability bound using only polylogarithmic repetitions. We should expect that BPP and PP are actually quite different classes. And that's the next result. So I'm just discussing that slide, but we will do the proof next time. So that's a recap of what we did. The BPP class required a probability of success, so of the right answer of 1/2 plus epsilon. But as we've just proved, we can essentially amplify that probability to any constant in delta without even affecting the running time by more than a constant. And we showed much more because we showed that we can actually bound it by some delta that goes to 1 exponentially fast in a sense, or superpolynomially fast. And we could, for example, define BPP so that we require 2/3 instead of 1/2 plus epsilon, or any other constant delta that doesn't change that class. The same is for the ZPP, for the Las Vegas algorithms. We've also seen how to amplify the probability of success there by essentially just repeating the algorithm a few times until it outputs something else than question mark. Okay. Whereas for unbounded errors, this was not possible. And here's the second reason why unbounded error and bounded error are very different. This class PP contains all of NP and all of co-NP. So it's very unlikely that this one is the same as P, even though the name is kind of PP and P. It's kind of similar, but So these are, this is a very mighty class, and the option to have such a weak bound on the success probability allows you to essentially simulate all kind of non-deterministic computations, which in turn also means that an algorithm with an unbounded error, Monte Carlo, in the Monte Carlo sense, is not helpful in any way. It's as good as a non-deterministic Turing machine, which we also can't use efficiently in practice. And, well, the proof we will do next time.